right now, pause whatever you're doing and reach into your pocket. Or open your wallet. Go ahead, find a coin. Any coin. It doesn't matter if it's a 5-cent piece from your change at the gas station, a dime you fished out from between the couch cushions, or a coin you've been carrying around for months without a second thought. Hold it. Feel the weight of it between your thumb and your index finger. Look at it. Really look at it. Because that dull, unassuming little disc you're holding right now is not what you think it is. It is a fragment of a dead star. It is a piece of cosmic shrapnel that has been falling through space for longer than the sun has existed. It contains a metal that medieval miners believed was placed on Earth by a goblin, a genuine, malicious supernatural creature, whose sole purpose was to drive men to madness and death underground. And today, that same metal, the one in your hand, is sitting at the absolute center of the biggest technological race of the 21st century. It is inside your phone. It is inside the battery of every electric car trying to save the planet from climate collapse. It is inside the jet engine of every commercial airplane crossing the sky above your head at this exact moment. The name of that metal is nickel. And if you think you know what nickel is, a cheap coin, maybe a corrosion-resistant coating on something shiny, then I promise you, by the time this story is over, you will realize you didn't know anything at all. Here's the first thing that should unsettle you. That 5-cent coin, the one Americans have casually called a nickel for generations, barely contains any nickel at all. It's mostly copper. The irony in that fact goes so deep, it almost feels like the metal is laughing at us. Nickel has been tricking human beings from the very beginning, hiding inside things that look like something else entirely, masquerading as copper in the mountains of medieval Saxony, disguising itself as simple rock when it's actually stardust, pretending to be just a cheap industrial filler when it is, in fact, one of the most strategically critical materials on the face of the Earth. Today, we are going to trace the full arc of this extraordinary element, from the nuclear furnaces of dying stars, where every nickel atom was forged billions of years before the Earth existed, all the way through the fire-soaked history of discovery, through wars and industrial revolutions and ecological disasters, all the way down to the bottom of the Pacific Ocean, where robotic machines are right now preparing to hoover up ancient mineral deposits from the seafloor in ways that could shatter entire ecosystems we haven't even fully discovered yet. This is the story of nickel, and it begins in darkness. Picture the year 1694, the Erzgebirge Mountains in what is now the eastern border region of Germany and the Czech Republic, in the old mining heartland of Saxony. The air smells of pine resin and iron-cold water. It is early morning, and a group of miners, big-shouldered, soot-faced men in leather breeches, are descending into a shaft they've been working for weeks. These men know mines the way farmers know fields. They read the rock. They understand veins and faults and the subtle color language of ore, the way a streak of green and gray stone means copper, the way red iron oxide bleeds out from between limestone layers like a wound. So when they find it, the vein, their hearts actually quicken. The color is right. A warm, brownish red, almost glowing in the lamplight. Copper-colored ore. Rich, dense, heavy. This is exactly what they've been looking for. They chip away samples, carry them up to the light, weigh them in their calloused hands with the practiced confidence of men who have done this 1,000 times before. And then they smelt it. They build the fire, they feed it ore, they work the bellows until the temperature climbs to the necessary heat. And they wait, and wait, and nothing comes out. No copper, not a single thread of red metal pours from the furnace. Instead, the process fills the air with a vile, acrid smoke, a choking, invisible presence that burns the throat and makes men's eyes water and gives some of them headaches so violent they have to be carried out into the forest to recover. The ore is not just useless, it is actively hostile. And here is where the story takes a turn into something that tells you a great deal about the human mind under pressure. These are not stupid men. They are skilled tradespeople, professionals in a dangerous industry. But they are also men of their time, a time when the forces of the natural world were still explained through the lens of the supernatural, and so they reach for the explanation that their culture has given them. This is not geology, this is malice. Someone, or something, has put this ore here specifically to ruin them. And the name they reach for is nickel, Old Nick, a mischievous, wickedly cunning underground spirit, a kobold, the Germanic tradition's version of a goblin, who delights in tricking miners. The demonic prankster who swaps real treasure for fake, who salts the rock with false promise, and then laughs as the men above ground tear their hair out in fury and confusion. They named the ore Kupfernickel, copper nickel, the devil's copper, Nick's copper, copper that isn't copper, courtesy of Old Nick himself. The word carries the full weight of their frustration. It isn't just a name, it's a curse. Now, before you laugh at these men for their superstition, consider what they were actually dealing with. The ore we now call nickelite, or nickeline, is a nickel arsenide mineral, meaning it contains arsenic bonded directly to the nickel. When you try to smelt it at high temperatures, the arsenic doesn't just stay in the furnace, it vaporizes. It rises in the smoke. Arsenic trioxide. Invisible, odorless at certain concentrations, and acutely toxic. These miners were being poisoned, repeatedly, by an ore that gave them nothing in return and was literally trying to kill them, visit after visit, month after month, year after year. The belief that it was cursed wasn't irrational mysticism, it was pattern recognition. Every time we touch this stuff, people get sick. Every time we try to use it, it fails. Something is wrong here that we cannot explain. The supernatural framework was wrong, but the empirical observation underneath it, this material behaves unlike anything else and causes harm, was completely accurate. In the mining communities of Saxony, Kupfernickel developed a reputation that spread across the mountains like a dark rumor. Men who worked near it got ill more often. Some died. The ore became associated with bad luck so consistently that entire communities came to dread finding it in their tunnels. It was a source not of wealth, but of grief. And it sat there, stubbornly useless, for decades while the world around it mined copper and silver and gold and built fortunes from the earth. Then came Axel Fredrik Kronstedt. The year is 1751. Kronstedt is a Swedish chemist and mineralogist, a product of the new Enlightenment spirit that was slowly replacing demons with data across European science. He's young, methodical, and crucially, he's not afraid of the ore that everyone else has learned to despise and avoid. When Kronstedt gets his hands on a sample of Kupfernickel, he doesn't see a cursed stone. He sees a puzzle. He approaches it the way a surgeon approaches a difficult anatomy, with calm, systematic curiosity. He heats it. He treats it with acids. He observes the reactions with careful attention. And what he observes is this: the substance behaves like a metal. Not copper, not iron, not any known metal. Something new. He manages, through a process of careful reduction, to isolate a small amount of a silvery white metallic substance. Dense, lustrous, unlike anything previously cataloged. He names it after the ore that produced it, after the demon of the mines. He calls it nickel. Think about that naming decision for a moment. Kronstedt was a serious scientist in an age that prided itself on rational rigor. He could have given this new element a classical Latin name, as was the fashion. He could have named it after himself, as many discoverers did. Instead, he took the folk name, the name of a goblin, of a trick, of a curse, and he planted it permanently in the scientific record. There's a kind of mischievous poetry in that. He imprisoned the demon's name inside the element itself, as if acknowledging that whatever Old Nick was, he was at least responsible for this astonishing discovery. The demon of the mines had, through years of poisoning and frustrating an entire industry, accidentally introduced humanity to one of the most important elements on the periodic table. The irony is staggering. The so-called cursed metal, the fake copper, the worthless poison ore, turned out to be worth, in the long run, immeasurably more than the copper it had mimicked. And not only more valuable than copper in terms of industrial importance, but fundamentally different in nature. Nickel is not a derivative of copper, not a lesser version of it, not a consolation prize. It is its own extraordinary thing, with properties that copper could never dream of matching. But the miners of the Erzgebirge didn't live to see that vindication. For them, Old Nick won. He always wins. Until the moment he doesn't. Long before any Saxon miner ever chipped at a vein of Kupfernickel, long before Cronstedt sat at his laboratory bench isolating a new element with methodical patience. Before any human being on the surface of this planet had the slightest idea that an element called nickel existed, it was already here. It had arrived from somewhere unimaginably far away, traveling at tens of kilometers per second through the vacuum of space, and it had been delivering itself to Earth in spectacular fashion for billions of years. We need to go back, much further back than the Erzgebirge, back to the year approximately 1933 BCE, to the Valley of the Nile, to the Egypt of the New Kingdom, to the reign of a boy king whose name every schoolchild on Earth recognizes, Tutankhamun. When archaeologist Howard Carter opened the sealed burial chamber of Tutankhamun in 1922, he found the most intact royal tomb ever discovered in Egypt, a treasure so overwhelming in its scope and beauty that Carter reportedly stared into the torchlit darkness for a long, speechless moment before anyone could get a word out of him. Among the thousands of objects inside that tomb was a dagger. Not just any dagger. The blade of this particular weapon was rust-free, almost perfectly preserved after more than 3,000 years. It was iron, which was itself remarkable, because in ancient Egypt, iron was extraordinarily rare and more precious than gold. But when modern scientists recently subjected the blade to X-ray fluorescence analysis, they found something even more remarkable. The iron of the blade was not terrestrial iron. It contained a very specific alloy composition, roughly 11% nickel and about 0.6% cobalt, a ratio that does not occur naturally in any iron ore deposit on Earth. That composition is, however, precisely what you find in a class of meteorites called iron meteorites. The blade of Tutankhamun's dagger was forged from a meteorite, from a rock that fell from the sky, an object that began its journey, quite possibly, before the solar system itself existed in its current form. The ancient Egyptians knew this. In the hieroglyphic texts of the period, iron is referred to by a term that translates, roughly, as iron from the sky or metal of heaven. They understood, on some level, that this miraculous material came from beyond the Earth. It wasn't mined from the ground. It was gathered from impact sites, from the places where the sky had sent pieces of itself crashing into the desert, and they treated it accordingly, as something divine, as something too sacred for common use. Here's the science that makes all of this inevitable. When you form a planet out of a rotating cloud of gas and dust, the heavy elements sink. Iron and nickel, being among the densest common elements, fall toward the center during the planet's formation and stay there. This means that the iron that forms in the core of an asteroid, a small, rocky body orbiting the Sun, is rich in nickel. Not because something added nickel to it, but because in any cosmic body that undergoes this differentiation process, the iron and nickel arrive together, as partners, settling into the metallic interior as the rock cools over millions of years. When two asteroids collide, and they do, constantly in the asteroid belt between Mars and Jupiter, they shatter. The pieces scatter. Some of them eventually drift into Earth-crossing orbits and fall into our atmosphere as meteorites. When they do, they bring with them the iron-nickel signature of their parent body's core. This is why iron meteorites, essentially without exception, contain nickel. And this is why nickel content is one of the primary forensic signatures scientists use to authenticate meteoritic iron. You can take a piece of metal found anywhere on Earth and test its nickel content. If the ratio is right, if it matches the characteristic composition of an iron meteorite, you know it fell from the sky, regardless of when, regardless of where. This means that for the ancient peoples of Egypt, of Mesopotamia, of the Great Plains of North America and the forests of Europe, every iron tool made from meteoritic material was, unknowingly, a nickel artifact. Every sacred blade, every ceremonially important object fashioned from sky iron was an object containing nickel. People were working with nickel, shaping it, heating it, wearing it close to their bodies as a mark of divine favor, millennia before a Swedish chemist ever gave it a name. Now here is the part that should fundamentally rearrange your sense of scale. The Tutankhamun dagger is a famous and specific example, but it is just one small artifact from one specific culture. The reality is that meteorites have been falling on Earth for 4.5 billion years. For 4.5 billion years, space rocks carrying iron-nickel alloy have been striking this planet, vaporizing on impact, scattering their metallic contents across the landscape, slowly, incrementally, contributing to the elemental composition of Earth's surface. Some scientists estimate that a small but meaningful fraction of the nickel in Earth's crust, not the bulk of it, which we'll get to in the next part of this story, but a real and measurable fraction, arrived via meteoritic bombardment during the planet's early history. This is what I mean when I say that nickel is a cosmic element. It's not a metaphor. It is literally true, in a geological and chemical sense, that a portion of the nickel we mine from the crust of the Earth traveled here through interstellar space as part of the debris field of an ancient, shattered asteroid. And here's the part that should sit with you for a moment. A thought that is either beautiful or deeply strange depending on your perspective. The nickel atoms in any given object you touch today were forged inside a star that no longer exists. Not in our star, not in the sun. In an older star, one that lived and died before the sun was born. When a massive star reaches the end of its life, it explodes in a supernova, one of the most violent events the universe is capable of producing. In the last seconds of that explosion, temperatures and pressures exist that are sufficient to fuse lighter elements together into heavier ones. Iron, cobalt, nickel. These elements are created in the final, catastrophic moments of stellar death. Then the explosion scatters them across space. Millions of years pass. Billions of years pass. The scattered material drifts. It joins gas clouds. It participates in the formation of new stars and new planetary systems. It ends up embedded in asteroids and meteorites. Some of it crashes into a young planet called Earth. Some of that material, eons later, ends up in a blade buried with an Egyptian pharaoh. Some of it ends up in a battery powering an electric car. Every single nickel atom on this planet was created in the death throes of a star that exploded before our solar system was born. The next time you hold a coin, even a coin that's mostly copper, and you feel that slight heft, that density, that cool metallic indifference against your skin, remember what it actually is. You are holding stardust. You are holding the ash of a dead sun. Now we need to go in the opposite direction, not out into space, but down. Down through layers of rock and time to a place no human being has ever visited and never will. Down through the crust of the Earth, past the deepest mines humans have ever drilled, past the depths where rock begins to flow like thick syrup under unimaginable pressure, past the boundary called the core-mantle interface, to a place roughly 2,900 kilometers beneath your feet. This is the outer core of the Earth. It is a sphere of liquid metal roughly the size of Mars. It is hot, between 4,000 and 5,000 degrees Celsius, hotter than the surface of the sun. And it is made primarily of two elements, iron and nickel. Nickel is not just an incidental component of the Earth's core. It is one of the two principal materials that make up the metallic heart of the entire planet. The Earth's core is, in a very literal sense, a gigantic ball of iron and nickel, roughly comparable in volume to the planet Mars. And this creates the central geological paradox at the heart of nickel's story on Earth. Here is the paradox. Nickel is the fifth most abundant element in the Earth as a whole. If you could take the entire planet, crust and mantle and core and all, and blend it into a single uniform composition, nickel would be present in significant quantities, more abundant than copper, more abundant than zinc, more abundant than many elements we consider common. But nickel is also, from the perspective of anyone standing on the surface trying to mine it, relatively rare. The concentration of nickel in the Earth's crust is only about 75 parts per million. That sounds like a lot until you compare it to iron, which makes up about 5% of the crust. Nickel is 1,000 times less concentrated in the places where we can actually reach it than it is in the places we can't. Why? Why did nickel abandon the surface? The answer lies in a process geologists call planetary differentiation, and it is one of the most dramatic events in Earth's entire history. When the Earth was young, 4.5 billion years ago, in the first 100 million years of its existence, it was not the solid, layered world we know today. It was a roiling, molten ball of rock and metal, thoroughly mixed together, superheated by the energy of formation and by the constant bombardment of other rocky bodies from the young solar system slamming into its surface. Everything was liquid. Everything was churning. There were no continents, no oceans, no crust of any kind. just an ocean of molten rock stretching from surface to center in constant violent motion. Then gravity did what gravity always does. It sorted things by density. The heavy materials, and nickel is heavy, with an atomic mass of 58.7 and a density about 8.5 times that of water, began to migrate downward through the molten mass. Iron was doing the same thing, and nickel has a chemical affinity for iron, which means they moved together. They are siderophile elements, literally iron-loving elements, and as the molten planet differentiated, they sank together toward the center in what geologists sometimes call the iron catastrophe. Though catastrophe makes it sound sudden, when in fact it took tens of millions of years. As this differentiation proceeded, the surface, the eventual crust, was progressively stripped of its nickel content. The heavy metals fell inward. The lighter silicate rocks rose. And the result, after the process was complete, was a planet with a thin, nickel-poor rocky shell wrapped around an enormous, nickel-rich metallic core. The crust we live on, the rocks we mine, the soils we farm, all of it is essentially the slag that was left behind after the valuable metals sank away. This means that if you want to understand why nickel deposits on Earth's surface are rare and localized, you have to understand that they are, in a sense, geological accidents, places where the normal outcome of planetary differentiation was disrupted. There are two main ways that enough nickel ends up concentrated in the crust to be worth mining. The first way involves exactly the kind of cosmic violence we discussed in the previous chapter, but on a vastly larger scale than a single meteorite. The single most productive nickel mining region in the world is Sudbury, Ontario, in Canada. And Sudbury exists because approximately 1.8 billion years ago, something roughly 10 to 15 kilometers across, a meteorite or small asteroid of extraordinary size struck the Earth at this location with a force equivalent to the detonation of roughly 100 billion nuclear weapons. The impact was so catastrophic that it shattered the crust, melted vast quantities of rock, and created what geologists call a multi-ring impact structure, a scar in the Earth's surface that, even after nearly 2 billion years of erosion and geological activity, is still plainly visible as an elliptical basin roughly 60 kilometers by 30 kilometers in size, the Sudbury Basin. But here's what makes Sudbury truly extraordinary from a mining perspective. The impact didn't just scar the surface. The violence of the collision drove magma, molten rock from the mantle, which is slightly richer in nickel than the crust, upward through the shattered rock. And as this magma cooled and crystallized, the iron-nickel-copper sulfides settled to the bottom of the magma chamber, concentrating in thick, mineable veins at the base of what geologists call the Sudbury Igneous Complex. The asteroid, in smashing into the Earth with incomprehensible force, had inadvertently served as a mining operation, punching a hole through the nickel-poor crust and dragging deeper, richer material up to a level where, 2 billion years later, human beings could get at it. Today, the Sudbury region has produced more nickel than any other single location in the world. The mining operation there has been running continuously since the 1880s. The infrastructure around the basin, the smelters, the refineries, the company towns, the railways, represents one of the most significant industrial landscapes in North American history. All of it exists because an asteroid struck the Earth 1.8 billion years ago. The second pathway for nickel to reach the surface in mineable concentrations involves not cosmic collision, but geological time and tropical weathering. In places like Indonesia, the Philippines, and New Caledonia, regions close to the equator with intense rainfall and geological conditions that produced ultramafic rocks, a different process operates. Rocks that are slightly richer in nickel than average crustal material, rocks called peridotites that come from the upper mantle, are exposed at the surface. Over tens of millions of years, the intense tropical rainfall attacks these rocks. The silicate minerals leach away. The nickel, which has a slightly different chemical behavior, is left behind and concentrated in a red, clay-rich layer called laterite. Laterite nickel deposits don't have the dramatic origin story of Sudbury. There was no apocalyptic asteroid, no billion-year geological saga, just rain. billions of years of patient, relentless tropical rain, slowly sorting through the rock and leaving the nickel behind like a sieve. But these laterite deposits now account for more than 60% of the world's known nickel reserves, and they are increasingly the source of the nickel feeding the 21st century's battery revolution. The irony of nickel's geological story is almost philosophical. An element abundant enough to be, by mass, one of the most significant components of the entire Earth is simultaneously rare enough on the surface that we have to rely on ancient asteroid impacts and millions of years of tropical erosion to accumulate enough of it to be economically viable. The planet is almost entirely made of nickel, in the sense that the core is full of it, and yet, to find a mine, you need either a billion-year-old crater or a tropical jungle. There is a vast reservoir of nickel sitting 2,900 kilometers beneath your feet right now. You will never reach it. Nobody will ever reach it. The pressure and temperature down there are so extreme that the concept of mining is simply inapplicable. That nickel, that gigantic sphere of liquid metal spinning at the center of the Earth and generating the magnetic field that protects all life on this planet from solar radiation, that nickel is as inaccessible as the surface of a neutron star. So we look for the scraps, the accidents, the places where cosmic violence or geological patience has pushed a little of what should have stayed deep up to where we can find it. And when we do find it, we dig. Lord, do we dig. Picture a forest so dense and so ancient that the canopy above you blocks out the sun completely. The air is wet and heavy with the smell of decomposing leaves and living earth, a heat that presses against you from every direction. The calls of birds you cannot name echo through the undergrowth. The soil beneath your boots is a deep, rusty red, the color of old blood, or of the planet Mars, or of the laterite deposits we talked about in the last chapter, because that is exactly what you were standing on. You were in the interior of the island of Sulawesi in Indonesia, and you were about to watch this forest disappear. Not slowly, the way forests usually disappear, not over decades of gradual encroachment by farms and settlements. This forest is going to disappear fast, the way a building disappears when the demolition crew arrives on a Monday morning with machines the size of houses. Sulawesi is the epicenter of something that does not have an official name yet, but probably should. Call it the Second Nickel Rush, or the Green Gold Rush, or perhaps the most profound environmental contradiction of the 21st century. Here is the contradiction in its starkest form. The world has decided, quite correctly, that burning fossil fuels is causing a climate catastrophe, and the most powerful technology we have developed to stop that catastrophe is the electric car. And the electric car runs on a battery, and that battery, the kind of high-capacity, high-energy density lithium-ion battery that powers an electric vehicle, requires nickel. A lot of nickel. A single large electric vehicle battery pack can contain anywhere between 30 and 100 pounds of nickel, depending on the battery chemistry. This means that the global transition to electric vehicles, which almost every government on Earth has committed to in some form, will require an enormous and rapidly escalating supply of new nickel. And where is most of the world's new nickel coming from? It is coming from Indonesia. Specifically, it is coming from the laterite deposits of Sulawesi, Halmahera, and other Indonesian islands. Deposits sitting beneath exactly the kind of ancient tropical forest that absorbs carbon from the atmosphere and supports biodiversity that took millions of years to evolve. The scale of what is happening there right now is genuinely difficult to comprehend if you have not seen it. These are not small operations. The open-pit mines being developed in Sulawesi are not the quaint, hand-dug shafts of the Saxon Erzgebirge. They are industrial landscapes measured in square kilometers. The topsoil and forest above the laterite layer, everything that lives there, everything that has lived there for millions of years, is stripped away by machines. Enormous excavators and dump trucks the size of houses work in shifts around the clock, removing overburden, the geological term for the living world that sits inconveniently on top of the ore. The laterite itself is then either smelted in nickel pig iron furnaces, a process that is extraordinarily energy intensive and was, until recently, typically powered by coal, or processed through high-pressure acid leaching facilities that produce the battery-grade nickel sulfate that battery manufacturers actually want. Both processes produce waste, large amounts of it. The waste from nickel laterite processing is called tailings, a mixture of water, acids, and heavy metal-contaminated sediment. And in some operations in the region, this material has historically been discharged into river systems or coastal waters. The rivers run red, the color of the laterite, threading through what used to be forest on their way to bays and reefs. The marine ecosystems downstream from active nickel processing operations have been shown in multiple studies to suffer measurable declines in biodiversity. Seagrass meadows disappear. Coral coverage decreases. The fish that local communities have relied on for protein for generations become scarcer. Now consider New Caledonia, the French territory in the South Pacific, which holds roughly a quarter of the world's known nickel reserves. New Caledonia is an island of extraordinary biological uniqueness. Because it has been geologically isolated for roughly 66 million years, since around the time the dinosaurs went extinct, it has evolved a flora and fauna found nowhere else on Earth. More than 3,000 species of plants grow there, and roughly 3/4 of them are endemic, meaning they exist nowhere else in the world. The island's nickel laterite deposits happen to coincide with much of its most unique and irreplaceable biological territory. The mining history of New Caledonia stretches back to the 1870s, and the landscape of the main island today reflects that history in a way that is visible from the air. Vast swaths of reddish-orange stripped earth contrasting with the remaining green of the forest, like a body with patches of skin removed. The indigenous Kanak people, whose culture and spiritual connection to the land predates European arrival by thousands of years, have been fighting for decades to balance their community's economic needs with the preservation of a landscape that is, for them, not just ecologically important, but cosmologically significant. The land is not just where they live, it is what they are. And into this tension, the 21st century's battery economy has arrived, with the force and subtlety of a wrecking ball, dangling enormous investment and employment opportunities in front of communities that have often been economically marginalized, while simultaneously threatening the environmental foundations of their traditional way of life. There is a question that lurks underneath all of this that nobody in the technology industry particularly likes to ask out loud. What is the actual carbon cost of manufacturing an electric vehicle, when you factor in not just the energy used in the factory, but the energy used to mine, smelt, refine, and transport the nickel in the battery? The honest answer is complicated. Electric vehicles do, over their operational lifetime, produce significantly less carbon than equivalent gasoline vehicles, even accounting for manufacturing. The math works out, eventually. But the math requires you to abstract away from the specific places and specific living systems that are sacrificed to make that math possible. It requires you to average across the entire global fleet of electric vehicles and measure net carbon reduction, rather than standing in the red mud of a clear-cut hillside in Sulawesi and asking the specific birds that used to nest in the specific trees that used to stand there whether they feel saved by the global carbon balance sheet. The people raising these concerns are not anti-progress. They are not oil industry lobbyists trying to slow the transition away from fossil fuels. They are ecologists. They are indigenous rights advocates. They are community members in the mining regions themselves. And they are asking a question that deserves to be taken seriously. Is it possible to build a clean energy future on a foundation of ecological destruction? And the uncomfortable truth is that right now, in the jungles of Sulawesi and on the red hillsides of New Caledonia, we are doing exactly that. The forest is coming down. The rivers are running red. The machines are working 24 hours a day, 7 days a week. And somewhere, a car rolls silently off a production line, and its owner feels good about the planet. This is the green paradox, and it does not have a clean resolution. Not yet. Let's come in from the global and go personal for a moment. Let's talk about you. Specifically, let's talk about your skin. Do you own a piece of jewelry that you cannot wear for more than a few hours without developing an irritating, itchy rash exactly where the metal touches you? Have you ever wondered why the button on the waistband of a pair of cheap jeans seems to leave a red mark on your belly? Have you ever noticed that certain earrings are fine and certain others make your earlobes swell up like something bit you? If any of these sound familiar, there is a very good chance you have a nickel allergy, and if you do, you are not alone. Not by a long shot. Nickel allergy is the single most common contact allergy in the industrialized world. Depending on which population study you look at, somewhere between 8 and 17% of women and between 1 and 3% of men in Western countries test positive for nickel sensitization. In absolute numbers, that translates to tens of millions of people in the United States alone who have an immune system that has been trained through repeated exposure to recognize nickel ions and respond to them with inflammation. The disparity between men and women has historically been attributed to jewelry-wearing habits. Women have traditionally worn more metal jewelry, especially pierced earrings, which creates direct contact between nickel-containing metal and the sensitized tissue inside a piercing. A piercing is a wound that heals around a piece of metal, and if that metal releases even trace quantities of nickel ions, which many lower-grade alloys do, the immune system gets an extended, intimate education in what nickel smells like, so to speak. And some immune systems decide they don't like the smell and mount a response. This response, once established, is permanent. There is no cure for nickel allergy. Once your immune system has learned to react to nickel, it will react to nickel for the rest of your life. Which matters because nickel is absolutely everywhere. It is in costume jewelry, obviously, but it is also in the clasps of bras, and the studs on jeans, and the frames of eyeglasses, and the buckles of belts, and the handles of kitchen utensils, and the zippers of jackets, and the coins in your pocket. It is in certain foods. Nickel occurs naturally in whole grains, legumes, nuts, and chocolate at low levels. And for the most severely sensitized individuals, dietary nickel can trigger systemic reactions that go beyond the skin. The European Union has some of the toughest nickel regulation in the world, specifically because of the allergy burden. EU rules strictly limit how much nickel can leach from any item that comes into prolonged contact with skin. The United States has historically been more permissive, which is why American consumers are more likely to encounter allergy-triggering jewelry in everyday retail than their European counterparts. There is something darkly ironic about all of this. The metal that the Saxon miners called the devil's copper, the metal associated with trickery and deception from the very beginning of its human history, turns out to have one more trick up its sleeve at the most personal level imaginable. It hides in the things we love to wear, the things that make us feel beautiful or fashionable or put together, and it quietly teaches our immune systems to hate it. The demon is not just in the mind. The demon is on your wrist. Now, let's shift scenes from the intimately personal to the sweep of mid-20th century history, because nickel's story gets genuinely fascinating when it collides with the machinery of the Second World War. Here is a historical fact that most Americans have never thought about for even a single second. In 1942, the United States government decided that the humble 5-cent coin, the nickel, needed to stop being made of nickel. The reason was simple and urgent. Nickel was a strategic war material. Every ounce of nickel that went into making coins was an ounce of nickel that could not go into making armor plate for tanks, gun barrels, engine components for military vehicles, and the vast array of other metal hardware that a nation engaged in a global industrial war needs in staggering quantities. The War Production Board classified nickel as a critical material and placed it under strict allocation controls. The U.S. Mint, which at the time was producing enormous quantities of 5-cent coins, hundreds of millions per year, was directed to find a substitute. The solution the Mint arrived at was a somewhat peculiar alloy, 56% copper, 35% silver, and 9% manganese. Yes, silver. For 2 years, from 1942 to 1945, the United States government minted its smallest denomination silver coins since the 19th century, specifically to free up nickel for the war machine. These war nickels, as collectors now call them, are distinguishable from normal coins by a large mint mark placed above the dome of Monticello on the reverse, a P, D, or S for the Philadelphia, Denver, and San Francisco mints, respectively, and by a slightly different color and luster compared to the standard copper-nickel coins produced before and after the war. They were a quiet admission, pressed in metal and circulated in billions of pockets across the country, that the war had reached even into the most mundane corners of everyday life. Your grandmother's loose change was a casualty of global conflict. The nickel in her coin purse had gone to war. And here is where the history of nickel and the history of American military-industrial strategy intertwine in a way that illuminates something important about how modern industrial economies actually work. Canada, which is home to the Sudbury Basin, the largest known nickel deposit in the Western Hemisphere, was a critical supplier to the Allied war effort. The Canadian nickel company, Inco, which had been mining Sudbury since the 1880s and had grown into one of the largest mining operations in the world, became essentially a strategic supplier for Allied military production. The supply chain running from the red rock of the Sudbury Basin through Canadian refineries to American and British munitions factories was not just commercially important. It was a genuine front in the war, a logistical artery without which the Allied ability to produce armored vehicles, naval ships, and the countless other implements of industrial warfare would have been significantly constrained. Nickel, the devil's copper, the goblin's joke, the cursed metal that Saxon miners cursed and spat upon, had, by the middle of the 20th century, become so embedded in the material foundation of modern civilization that a war for the survival of that civilization could not be fought without it. The coin in your pocket was conscripted. The earth of Ontario was mobilized. Even Old Nick, it seems, could be drafted. Harry Brearley was having a frustrating year. The year was 1913. Brearley was a metallurgist working at a research laboratory in Sheffield, England. At the time, Sheffield was the steel capital of the world, the city where the Industrial Revolution had forged its hardest ambitions, a place that smelled permanently of hot metal and coal smoke, where the clanging of hammer on anvil was the city's heartbeat. Brearley had been tasked with a specific, rather unglamorous problem. The British Army was having trouble with the erosion of rifle barrels. The inside surfaces of rifle barrels wear away over time from the heat and friction of firing, and the Army wanted a steel that could withstand this erosion better than existing alloys. So Brearley was experimenting with different compositions of steel, adding various proportions of different alloying elements, chromium, nickel, carbon, manganese, in different combinations, casting small experimental ingots, analyzing them, discarding them when they didn't work, trying again. It was methodical, unglamorous laboratory work. Hundreds of experimental samples came and went. Most of them got tossed into a scrap pile in the corner of the lab. Rejected experiments, useless failures, the debris of the research process. At some point in the late summer of 1913, Brearley was clearing out the scrap pile. He noticed something odd. Most of the discarded steel samples had rusted, as steel does. A thin film of red-brown oxidation coating the metal's surface, the inevitable result of iron reacting with oxygen and moisture in the air. But one of the samples hadn't. One specific ingot, with a composition that included a significant chromium addition alongside nickel, sat there in the scrap pile looking exactly as bright and clean as the day it had been cast. Brearley picked it up. He examined it. He set it aside instead of throwing it away. He went back to his records, identified the composition. Roughly 12 to 13% chromium was the key, and began to investigate more systematically. What he had accidentally discovered in the scrap pile of a Sheffield laboratory was stainless steel, the material that would transform surgery, architecture, kitchen equipment, chemical engineering, food processing, transportation, and 100 other industries in the 20th century. The material without which the modern world, in very concrete and literal ways, would not be possible. The reason stainless steel doesn't rust is a phenomenon called passivation. When you add enough chromium to steel, roughly 10 to 11% is the minimum threshold. The chromium atoms at the surface of the metal react with oxygen in the air before the iron atoms can. The chromium creates a thin, transparent, extraordinarily adherent layer of chromium oxide on the surface of the steel. This passive layer acts as a barrier. It is self-healing. If you scratch the surface, the underlying chromium immediately reacts with oxygen and reforms the protective layer. The iron underneath never gets exposed to the corrosive environment. It stays pristine. Now, where does nickel fit into this? Because I have been building to this. Pure chromium steel, with just chromium and no other major additions, is actually somewhat brittle and difficult to work with. It is hard to roll, hard to weld, hard to form into complex shapes. The addition of nickel to the alloy changes this dramatically. Nickel stabilizes the crystal structure of steel in a way that makes it simultaneously tougher, more ductile, meaning it can be stretched and bent without cracking, and more resistant to corrosion at elevated temperatures. The most common grades of stainless steel used in everything from kitchen sinks to surgical instruments to chemical processing equipment contain both chromium and nickel in combination. The famous 300 series of austenitic stainless steels, the grades that account for roughly half of all stainless steel production worldwide, typically contain between 8 and 12% nickel alongside the chromium. Nickel is not an optional addition to these steels. It is the element that makes them workable, manufacturable, useful. Without nickel, stainless steel would exist only as a laboratory curiosity, a brittle, difficult-to-process material unsuitable for the industrial-scale production that made it the backbone of modern manufacturing. Brearley gets the credit for the discovery, and he deserves it. But the unsung hero of stainless steel's success story is the nickel atom sitting in the crystal lattice, making everything flexible. And this is a pattern that repeats throughout nickel's industrial history. Nickel rarely takes the starring role. It is almost always a supporting element, an additive, a modifier, the metal that makes other metals better. The metallurgical community has a phrase for this. Nickel is a toughener. Add it to steel, and the steel becomes less brittle. Add it to copper, and you get cupro-nickel, which is strong and resistant to corrosion by seawater, the alloy that is used to make the hulls of naval vessels and the condensers of power plants. Add it to cobalt-based alloys, and you get materials that maintain their strength at temperatures that would cause ordinary steel to soften and creep. But the most spectacular expression of nickel's role as the silent enabler of other materials is in the world of superalloys. And the story of how those superalloys came to exist is inseparable from the history of aviation and from the Second World War. A jet engine is one of the most thermally brutal environments that a manufactured object can experience. The turbine blades at the heart of a jet engine spin at thousands of revolutions per minute while being bathed in gases at temperatures that can exceed 1,500 degrees Celsius, hot enough to melt ordinary steel, hot enough to make aluminum glow and soften. For a jet engine to work at all, the turbine blades must maintain their structural integrity, their precise aerodynamic shape, and their mechanical strength at temperatures that would reduce most metals to a puddle. This requirement drove one of the most intensive materials science research programs in history, beginning in the 1930s and accelerating dramatically during the Second World War, as both the Allied and Axis powers raced to develop workable jet engines. The solution that emerged, after enormous effort and ingenuity, was a class of materials now called nickel superalloys. Alloys based on nickel, with additions of chromium, cobalt, aluminum, titanium, molybdenum, and other elements in carefully balanced proportions that can maintain their mechanical properties at temperatures where nothing else can. The most famous of these, Inconel, developed by the International Nickel Company in the 1940s, became essentially the defining material of the jet age. Every commercial jet engine flying today uses nickel superalloy turbine blades. Every military jet fighter, every spacecraft engine, every industrial gas turbine. Nickel is the reason that commercial aviation is possible. It is the reason that you can step onto a plane in New York and step off in London 8 hours later, carried by the controlled fury of engines that burn hotter than anything in the pre-industrial world, and yet run reliably for tens of thousands of hours before requiring major maintenance. The demon of the mines, the goblins trick, the cursed ore of Saxony. It holds civilization up, spinning in the fire, never failing. Quietly, invisibly, without recognition. That is nickel's character. That is what it does. The year is 2008, and in a gleaming conference room somewhere in the global electric vehicle industry, it could be Detroit, it could be Tokyo, it could be Shenzhen, a materials scientist is drawing a diagram on a whiteboard. The diagram shows the inside of a lithium-ion battery cell. There is an anode on one side, typically made of graphite. There is a cathode on the other side, and it is the cathode that the materials scientist is circling, again and again, with mounting emphasis, because the cathode is where the future lives or dies. In the early days of the modern lithium-ion battery, the cathode was typically made of lithium cobalt oxide, a material with excellent energy density and charge-discharge characteristics, but with one enormous problem: cobalt. Cobalt is scarce, cobalt is expensive, and the vast majority of the world's cobalt supply comes from a single country, the Democratic Republic of the Congo, where the mining industry has been plagued by extraordinarily serious human rights concerns, by conditions that range from deeply problematic to genuinely horrific. For a technology industry that aspired to build a clean, ethical supply chain for its products, cobalt was an ever-present scandal, a dark stain on every premium laptop and every electric car. So the battery industry went looking for ways to use less cobalt. And what they found, at the end of that search, was nickel. The battery chemistry that has come to dominate the high-performance end of the electric vehicle market is known as NMC, nickel, manganese, cobalt, in various ratios, or NCA, nickel, cobalt, aluminum. In both cases, the trend over the past 15 years has been unmistakable and unambiguous. More nickel, less cobalt. Early NMC cells used roughly equal ratios of the three metals. Then the industry moved to formulations with more nickel. 60% nickel became standard, then 80%, then higher. The current frontier of battery technology is the so-called high-nickel cathode, formulations where nickel makes up 90% or more of the cathode material, with cobalt reduced to a few percent or eliminated almost entirely. From the perspective of battery performance, more nickel is better in almost every way that matters to a consumer. Higher nickel content in the cathode correlates with higher energy density, meaning more range for a given battery weight. It correlates with better fast charging performance. It correlates with a battery that is more competitive as a product in a market where consumers are increasingly demanding vehicles that can travel 300 or 400 miles on a single charge and be recharged in 20 minutes at a highway charging station. From the perspective of the raw material supply chain, more nickel also means less dependence on Congolese cobalt, which is a genuine ethical improvement. So every direction the industry logic pushes, better performance, lower cobalt dependency, more competitive products, pushes toward nickel. More nickel. Much more nickel. And this is where the scale of what is coming begins to feel genuinely vertiginous. Global nickel production in the early 21st century runs at somewhere around 2.5 million tons per year. According to projections from the International Energy Agency and multiple independent research groups, meeting the battery demand implied by a full global transition to electric vehicles by 2040 or 2050 would require nickel production to increase by anywhere from 3 to 6 times current levels. To put that differently, humanity needs to mine more nickel in the next 20 to 25 years than it has mined in the entire history of nickel extraction combined. All of the mines, all of the operations, all of the tons extracted since the Saxon miners first cursed Kupfernickel in the 17th century, all of that added together is roughly the amount of additional nickel we need to find, mine, process, and deliver in the next 2 decades on top of current production. The scale of this demand is driving a geopolitical reshaping that most consumers are entirely unaware of. Indonesia, which holds the world's largest reserves of nickel laterite, has become the center of a massive industrial investment program backed largely by Chinese capital and technology. Chinese companies, working through the supply chain architecture of the battery and electric vehicle industry, have invested tens of billions of dollars in Indonesian nickel processing infrastructure. They have built nickel pig iron smelters, they have built high-pressure acid leach facilities, they have built the refining capacity to convert Indonesian laterite ore into the battery-grade nickel sulfate that cathode manufacturers need. Indonesia, recognizing the strategic value of what it sits on, banned the export of unprocessed nickel ore in 2020, forcing international investors to build processing capacity inside the country rather than simply shipping raw ore abroad. The result is the rapid emergence of an integrated industrial complex, mine to refinery to battery precursor material, concentrated in a single country, largely financed and technically operated by a single foreign power. If you are an electric vehicle manufacturer in Germany or South Korea or the United States and you need battery-grade nickel, the supply chain runs, to a significant and growing degree, through Indonesia and through Chinese-controlled processing operations. This is not a conspiracy. It is not a secret. It is visible in trade data, in corporate filings, in investment announcements. But it is also a strategic reality that Western governments and industries have been slow to fully reckon with. The race to decarbonize has created a new set of strategic dependencies, a new version of the energy vulnerability that the 20th century built around oil. And many of the nations most committed to the clean energy transition are only now beginning to fully understand the degree to which they have replicated, with different raw materials, the same geopolitical exposure they spent decades trying to escape. And underneath all of this strategic maneuvering and investment and geopolitical anxiety, the forest in Sulawesi is still coming down. The rivers are still running red. The machines are still working, shift after shift, in the tropical heat. Every decision made in a conference room in Shanghai or Berlin or Washington, D.C. reverberates, eventually, in the red mud of an Indonesian hillside. That is the chain. That is the true supply chain of the clean energy future. And most of the people who benefit from it never see the link at all. There is a place on Earth where the rules of biology seem to have been written by a different author entirely. Not the cautious, conservative author who designed most of life as we know it, the one who built organisms that require moderate temperatures, neutral pH, and a reliable supply of oxygen. This other author is stranger and more experimental. The organisms living in the places this author designed breathe sulfur compounds instead of oxygen. They thrive in temperatures that would denature the proteins of any ordinary cell within seconds. They live in liquids acidic enough to dissolve metal. And some of them, and this is where nickel enters the story again, from a direction you would never expect. Some of them use nickel not as a contaminant to be avoided, but as a tool, as a biological tool, as part of the chemistry of life itself. We tend to think of nickel as an industrial material, a metal, something smelted and rolled and machined. But long before human beings ever set foot on this planet, long before the first fish crawled onto land, long before the dinosaurs, long before almost anything we would recognize as complex life existed, nickel was already playing a role in the biochemistry of living organisms. The ancient, primitive metabolic pathways, the chemical reactions that the earliest life forms used to extract energy from their environment, are, in many cases, nickel-dependent. The enzyme urease, which breaks down urea and is found in a vast number of microorganisms and plants, requires nickel atoms in its active site to function. Without nickel, urease doesn't work. The enzyme hydrogenase, which allows certain microorganisms to use hydrogen gas as an energy source, a metabolic strategy that dates back billions of years to the early Earth, when the atmosphere was full of hydrogen, also requires nickel. The enzyme carbon monoxide dehydrogenase, which some microorganisms use to metabolize carbon monoxide and plays a role in the global carbon cycle, is a nickel enzyme. Methyl coenzyme M reductase, the enzyme responsible for the final step in the production of methane by methane-producing microorganisms called methanogens, the microbes responsible for a significant fraction of the methane in Earth's atmosphere, the methane that seeps from marshes and rice paddies, and the digestive systems of ruminants, that enzyme too has nickel at its catalytic core. Nickel, in other words, is woven into some of the most ancient and fundamental biochemical reactions on the planet. It is a trace element that life, at its most primordial level, learned to depend on long before the first complex multicellular organisms appeared. Now, let's take this biological story somewhere genuinely strange. In the deep ocean, at the mid-ocean ridges where tectonic plates pull apart and hot magma wells up from the mantle, there are hydrothermal vents, places where superheated water, loaded with dissolved minerals, erupts from the seafloor in billowing black or white clouds. The water coming out of these vents can reach temperatures of 300 to 400 degrees Celsius. The surrounding water is near freezing. The chemistry is chaotic and extreme, rich in hydrogen sulfide, methane, iron, and, yes, nickel. And clustered around these vents, in absolute darkness, at pressures that would crush a human being, are communities of organisms unlike anything found anywhere else on Earth. Tube worms, eyeless shrimp, giant clams, microbial mats of extraordinary density. These ecosystems run entirely on chemical energy rather than sunlight, a mode of life called chemolithotrophy, and nickel-dependent enzymes are central to the metabolic strategies of many of the microorganisms in these communities. Some archaea, single-celled organisms from the domain of life that is neither bacteria nor eukaryote, a domain whose members are some of the oldest lineages of life on Earth, have been found in hydrothermal environments actively metabolizing nickel compounds, using the metal as part of their energy extraction chemistry in ways that researchers are still working to fully understand. But here is the piece of this story that I want you to sit with for a moment, because it connects everything we've discussed so far in a way that feels almost like a closed loop. There are microorganisms found in the acidic drainage water of nickel mines, among other places, that have evolved to metabolize nickel-containing minerals directly. They oxidize metal sulfides, including nickel sulfide minerals, as part of their energy metabolism. They eat rock. Specifically, some of them eat the same nickel-containing minerals that human miners dig out of the earth. Some of these nickel-oxidizing bacteria have been found associated with meteoritic material, with the iron-nickel alloy of iron meteorites. Bacteria that eat meteors. Bacteria that consume the same stardust we talked about in Chapter 3. The chain from supernova to Saxon mineshaft to bacterial metabolism is not a metaphor. It is a literal sequence of physical events involving the same atoms. The nickel forged in a stellar explosion, incorporated into a meteorite, fallen to Earth, dissolved from the rock surface by acidic groundwater over millions of years. That nickel is food for microorganisms that have evolved specifically to consume it. Life finds nickel everywhere it has been deposited by the universe and figures out how to eat it. Now for the dark side of nickel's biological story, because there is one, and it is significant. We just established that nickel is a biologically essential trace element, required by certain enzymes, used by ancient metabolic pathways, incorporated into the chemistry of life at a fundamental level. And it is true that nickel deficiency in plants and animals can cause measurable physiological problems. Plants grown in nickel-deficient soils develop a condition called urea toxicity. They accumulate urea because urease can't function without nickel, and the urea buildup damages their tissues. Some animals show growth defects and metabolic abnormalities under conditions of nickel deficiency. But, and this is a very large but, nickel is also a proven human carcinogen. Not in its pure metallic form, not in the alloys used in everyday objects, but in specific chemical forms, specifically as nickel dust and nickel compounds inhaled in occupational settings. Workers in nickel smelters and refineries who are exposed over years to airborne nickel compounds show significantly elevated rates of lung cancer and nasal cavity cancer. The International Agency for Research on Cancer classifies nickel compounds as Group 1 carcinogens, the highest classification, meaning the evidence for human carcinogenicity is considered sufficient and conclusive. This is the biological paradox of nickel rendered in its sharpest form. An element that life evolved to use, that sits at the heart of ancient biochemical machinery, that microorganisms have been metabolizing for billions of years, is also, in the wrong form at the wrong exposure level, capable of causing cancer in the human beings who mine and process it. The element that is essential at trace levels in the soil, that allows plants to process nitrogen compounds and grow, that allows ancient archaea to breathe at the bottom of the ocean. That same element, turned into a fine dust and breathed into human lungs day after day for years, rewrites the cellular instructions in lung tissue with potentially fatal consequences. This duality is not unique to nickel. Many essential trace elements, selenium, chromium, even iron, are beneficial or necessary at low levels and toxic or carcinogenic at high ones. But nickel's duality is particularly dramatic, spanning the full range from ancient biochemical necessity to industrial occupational hazard, from the enzyme in the root nodule of a legume to the cancer ward of a hospital near a nickel refinery. Old Nick plays both roles with equal facility, the giver of life at one scale, the taker of it at another. The demon of the mines was never just a metaphor. Now I want to take you somewhere that almost no human being has ever seen, and that fewer still will ever see in person. I want to take you to the bottom of the Pacific Ocean. Not the dramatic bottom of the Mariana Trench, not the deepest point, the place of extreme geological drama that has claimed most of the public attention for deep-sea exploration. I want to take you somewhere in some ways more remarkable. A broad, flat, essentially featureless abyssal plain that lies between about 4,000 and 5,500 meters below the surface, in the region of the Pacific Ocean between Hawaii and the coast of Mexico. This region is called the Clarion-Clipperton Zone, and on the floor of the Clarion-Clipperton Zone, covering an area roughly the size of the continental United States, there are rocks. Not dramatic rocks, not jagged volcanic formations or cathedral-like hydrothermal structures, just rocks. Lumpy, roughly potato-shaped, dark brownish-black rocks, ranging from the size of a marble to the size of a bowling ball, scattered across the seafloor in dense fields with a coverage that, in places, can approach nearly complete. These objects have a name, polymetallic nodules, and they are extraordinary. Each nodule forms over millions of years, some of them over tens of millions of years, by the slow, almost impossibly gradual accretion of metal compounds layer by layer around a tiny nucleus. The nucleus might be a shark's tooth, a fragment of a basalt rock, a piece of shell. Around this nucleus, dissolved metals from the seawater above and from the sediment below precipitate out and deposit themselves, layer upon concentric layer, at a rate of somewhere between 1 and 10 millimeters per million years. To put that in perspective, the rate at which these nodules grow is so slow that in the time it takes a human fingernail to grow across the width of your finger, a polymetallic nodule grows by roughly the thickness of a human hair. They are among the slowest growing objects on Earth, and they are absolutely loaded with nickel. A typical nodule from the Clarion-Clipperton Zone contains roughly 1 to 2% nickel by weight, along with significant concentrations of cobalt, copper, and manganese. By the standards of terrestrial ore deposits, these concentrations are not spectacular, but the total quantity of material is. The Clarion-Clipperton Zone alone is estimated to contain somewhere in the range of 300 million to 800 million tons of polymetallic nodules, enough to represent one of the largest known concentrations of battery-relevant metals anywhere on or in the planet. The total quantity of nickel sitting on the floor of the Clarion-Clipperton Zone is estimated to exceed the total known nickel reserves in all terrestrial deposits combined. We have been mining nickel on land for more than a century. We have dug into the Sudbury Basin. We have stripped the laterites of Sulawesi. We have processed the ore and refined the metal, and shipped it around the world and built civilization with it. And sitting 4,000 meters below the surface of the Pacific Ocean, growing at the speed of a human hair per million years, untouched and virtually unstudied, is more nickel than all of that put together. The question, obviously, is whether we should go get it. And the answer to that question is one of the most ethically and scientifically complex issues in the entire story of nickel. Here's what we know about the Clarion-Clipperton Zone as an ecosystem. It is not empty. The nodule fields, despite existing in complete darkness at crushing pressure, with essentially no food supply falling from above, except for the slow, thin rain of organic particles drifting down from the sunlit ocean surface 4 kilometers up, support a community of organisms. Some of these organisms are attached to the nodules themselves: sponges, corals, sea cucumbers, brittle stars, polychaete worms, and are dependent on the hard substrate the nodules provide for their attachment, in a world where the surrounding sediment is so soft and fine that it provides no purchase for anything that needs to anchor itself. Some of these organisms are extraordinary. The depths of the Clarion-Clipperton Zone harbor species that produce their own light in the absolute darkness. Organisms whose biology is so poorly understood that science has not yet fully described them. Glass sponges that can live for hundreds or possibly thousands of years. Xenophyophores, single-celled organisms that can grow to the size of a dinner plate, making them among the largest known individual cells in nature. Communities of microbial life living in and on the nodule surfaces, whose metabolic capabilities we have barely begun to characterize. And here is the crucial ecological fact. The nodule fields are the ecosystem. The hard substrate of the nodules is what makes the ecosystem possible in an environment where everything else is liquid mud. If you remove the nodules, you remove the foundation of the community. Unlike most terrestrial mining, where you extract ore from the ground and the surface ecosystem, while damaged, has some potential to recover over human timescales, The Clarion-Clipperton Zone ecosystem operates on timescales that make recovery essentially meaningless from any human perspective. The nodules, remember, grow at 1 to 10 millimeters per million years. A nodule that took 20 million years to form and is removed by a mining machine cannot be replaced on any timescale relevant to human civilization. The ecosystem that depended on it is, for all practical purposes, permanently gone. We know this because we have already tested it in a small way. In 1978, a test mining operation scraped a small patch of nodule field in the Indian Ocean and then monitored the recovery. Decades later, 26 years later, as of the most recent reported survey, the nodule field had not recovered. The organisms that had lived on the nodules were not coming back because the nodules were not coming back. The test scar was still clearly visible on the seafloor, dead and bare, a quarter century after a small, limited experimental disturbance. Now consider what the commercial mining industry is proposing. Not a small experimental patch, but industrial extraction across hundreds of thousands of square kilometers, using machines the scale of multi-story buildings that would vacuum up the seafloor, separate the nodules aboard processing ships, and return the fine sediment in a slurry plume that could drift for hundreds of kilometers, smothering nodule fields and organisms far from the mining area itself. The International Seabed Authority, the United Nations body responsible for regulating deep-sea mining in international waters, has been developing regulatory frameworks for years, under pressure from both commercial interests eager to begin extraction and scientific and civil society voices urging extreme caution. Multiple countries and corporations have already obtained exploration licenses covering vast areas of the Clarion-Clipperton Zone. Some have been conducting equipment tests. The technology, the capital, and the commercial logic are all pointing in one direction. And on the other side of the argument are marine biologists, ecologists, indigenous Pacific communities, and a growing number of technology companies, including some battery and vehicle manufacturers, who have declared moratoriums on the use of deep-sea mined minerals in their products, at least until adequate environmental safeguards are established. The tension here is not simply economic versus environmental. It is a genuine question about what we value and how we measure value across time. The battery economy needs nickel. The world needs to decarbonize. The Clarion-Clipperton Zone contains enormous quantities of nickel, and the Clarion-Clipperton Zone also contains one of the largest and least disturbed deep-sea ecosystems on the planet, full of organisms that took millions of years to evolve and that we understand only partially, existing in a darkness and silence so profound and so removed from human experience that it constitutes, in a real sense, an alien world sitting at the bottom of our own ocean. We are standing at a decision point. The machines are ready. The companies have their licenses. And 4,000 meters below the surface, in the cold dark, the glass sponges and the xenophytophores and the luminescent worms are going about their ancient, slow business, utterly unaware that far above them, on the bright surface of the planet, a species that has been here for the blink of a geological eye is trying to decide whether they should survive the next century. The story of nickel has taken us, over the past several chapters, to some dark places, to stripped forests and red rivers, to the lungs of smelter workers and the scarred floors of test-mined ocean beds, to the geopolitical maneuvering of great powers over a metal that powers the devices in our pockets and the vehicles in our driveways. And, if you have been paying attention, you might have arrived at a feeling of something close to despair. The scale of the demand is enormous. The environmental costs of supply are severe. The timelines for building new mines are long. The alternatives seem inadequate. This is the story as it looks in the darkest light. But I want to offer you something else. Not false optimism. Not the kind of reassuring handwave that says technology will sort it all out and you don't need to worry. I want to offer you a genuine, complicated, uncertain but real picture of the ideas and approaches that are being pursued right now to try to untangle the knot of the nickel paradox. The first and most important of these is recycling. And when I say recycling in this context, I don't mean the casual, half-hearted gesture of putting a bottle in a blue bin. I mean the emergence of what industrial ecologists call the circular economy for battery materials, a system in which the nickel, cobalt, lithium, and manganese in a battery at the end of its life are recovered and returned to the supply chain as input for new batteries, rather than discarded. The chemistry of lithium-ion batteries makes them, in principle, highly amenable to recycling. The cathode materials in a spent battery contain nickel, cobalt, and manganese in concentrations that are actually higher than in most natural ore deposits. A pile of used electric vehicle batteries is, from a materials perspective, a higher-grade ore than a nickel laterite mine in Sulawesi. The technical processes for recovering these materials exist and work. Hydrometallurgical processes using acidic solutions to dissolve the cathode material and selectively recover each metal, or direct recycling approaches that aim to recover the cathode material in its original crystal structure without breaking it down all the way to individual metals. Companies specializing in battery recycling, a small but rapidly growing industry, are building facilities in North America, Europe, and Asia. Some of the largest battery manufacturers in the world have committed to closed-loop supply chains in which they take back their own spent batteries, recycle the materials, and reuse them in new production. The economics of battery recycling are currently challenged. It is often cheaper to buy virgin material than to recover recycled material, especially when raw material prices are low. But the economics change as battery volumes grow. Each year that passes, there are more spent batteries entering the waste stream. The mountain of urban ore is growing, and as the first generation of mass-market electric vehicles reaches the end of its useful battery life, in the late 2020s and into the 1930s, the recycling industry will face its first major test of scale. What happens in those years? Whether the recycling infrastructure builds fast enough to capture a significant fraction of the material will determine whether battery recycling becomes a genuine pillar of the nickel supply chain or remains a peripheral contribution. But there is a second approach to the nickel paradox that is so strange, so counterintuitive, so genuinely at the boundary between agriculture and mining that I want to spend some time with it. It is called phytomining, or more precisely, phytoextraction of metals, the use of plants to extract metals from soil. The key to understanding phytomining is a category of plants called hyperaccumulators. These are plants that have evolved in response to growing in soils with naturally elevated metal concentrations, the ability to take up metals from the soil through their roots at extraordinary rates and concentrate them in their above-ground tissues, their leaves and stems, at levels that would be toxic to any ordinary plant. There are more than 700 known plant species that hyperaccumulate nickel. Most of them are small, unassuming wildflowers and shrubs, members of genera like Alyssum and Nokia and Renoria, many of them native to the ultramafic soils of the Mediterranean, the Balkans, or Southeast Asia, the same types of nickel-rich soils derived from mantle rocks that we discussed in the geological chapter. These plants have evolved to not just tolerate the high nickel concentrations in their native soils, concentrations that are genuinely toxic to most plants, but to actively accumulate nickel in their tissues at concentrations that can reach 1%, 2%, even in extreme cases more than 3% of their dry weight. A plant that is 3% nickel by dry weight is not a plant. It is a low-grade ore deposit that grows, photosynthesizes, reproduces, and takes carbon out of the atmosphere while it does so. The concept of phytomining nickel is simple, even if the practical implementation is challenging. Grow hyperaccumulator plants on nickel-rich soils, harvest the above-ground biomass when nickel concentrations peak, burn or chemically process the biomass to recover the nickel as a concentrated ash or leachate, and repeat. The soil is left in place. The ecosystem is not destroyed. The process uses solar energy rather than diesel fuel. The plants capture carbon from the atmosphere while they grow, partially offsetting the carbon footprint of the nickel recovery process. Research programs in France, the United Kingdom, Malaysia, and elsewhere have demonstrated that phytomining can work in principle. Under favorable conditions, with well-selected hyperaccumulator species on suitable soils, researchers have recovered nickel at costs that are beginning to approach economic viability for niche applications. The word beginning is doing significant work in that sentence. The honest assessment of where phytomining stands right now is that it is a proven concept that is nowhere near the scale required to make a meaningful dent in global nickel demand. The yields are low. The logistics of harvesting and processing large quantities of low-density plant biomass are challenging. The soils suitable for phytomining, ultramafic soils with naturally elevated nickel concentrations, while not rare, are also not infinite. A phytomining operation that might produce tens of tons of nickel per year occupies land and resources that a conventional mine would use to produce tens of thousands of tons. But here is why phytomining still matters, why researchers are still pursuing it, why it belongs in the same conversation as deep-sea mining and battery recycling when we talk about the future of nickel supply. It matters because it represents a fundamentally different relationship between resource extraction and the living world. Every other nickel extraction method we have discussed, conventional open-pit mining, deep-sea nodule collection, even some forms of in-situ leaching, involves the destruction or severe disruption of the ecosystem in the extraction zone. Phytomining, if it can be made to work at scale, would be the first large-scale method of metal extraction that is not just compatible with a functioning ecosystem, but that actually requires one. The plants need to grow. The soil needs to be alive. The process is, in a meaningful sense, farming for metal rather than mining for it. It will not save us by itself. Nothing will save us by itself. The nickel paradox does not have a single elegant solution. It has a set of partial solutions: recycling, phytomining, better battery chemistry, demand reduction through longer battery lifetimes and lighter vehicles, and yes, some continued conventional mining subject to genuinely enforceable environmental and social standards that together might, if pursued with sufficient urgency and intelligence and political will, add up to something livable. The real battlefield, as this story approaches its end, is not in the mines or on the seafloor. It is in the minds of the engineers working on lithium iron phosphate batteries, a chemistry that requires no nickel, no cobalt, that is cheaper to manufacture and already competitive in energy density for many applications. The rapid rise of lithium iron phosphate technology in China and its accelerating adoption in markets around the world is perhaps the most significant single development in the effort to reduce the clean energy transition's dependence on nickel. Not because nickel will disappear from batteries. High-energy density applications will likely continue to prefer nickel-rich chemistries for years to come. But because the emergence of a viable, scalable nickel-free alternative changes the terms of the negotiation. It means that demand for nickel is not a fixed and inevitable number, determined by how many electric vehicles the world chooses to build. It is a variable, shaped by which battery chemistries win in which market segments, by how fast recycling infrastructure is built, by how aggressively vehicle manufacturers pursue battery weight reduction and lifetime extension. The demon is not inevitable. The demon can be bargained with. Maybe. Go back to your pocket. Go back to the coin. Pick it up one more time and hold it in the light. Look at it differently now. This small, dull, humble object has traveled further than you can imagine to reach your hand. The nickel atoms in it, and yes, even in a coin that is mostly copper, there are nickel atoms, because nickel is everywhere now, woven into the metal world we have built around ourselves. Those atoms were forged in the core of a star that died before our solar system was born. They drifted through space as part of the debris cloud of a shattered asteroid. They fell to Earth in meteorites, some of them landing in the Egyptian desert, where priests of a civilization 3,000 years gone gathered them up as sacred objects fallen from the sky. Some of them sank in the planet's molten youth toward the center of the Earth, joining the vast metal ocean that still spins down there in the dark, generating the magnetic field that stands between all life on this surface and the killing radiation of the sun. Some of them were pushed back up to the surface by the violence of asteroid impacts. The Sudbury crater, the geological memory of a cosmic collision that nobody witnessed and whose scale would be incomprehensible to any human observer. Some of them were dissolved out of tropical rock by 1 billion years of equatorial rain. Some of them were dug out of the earth by Saxon miners who called them cursed, who believed that a goblin had put them there specifically to deceive and to harm. Some of them were isolated in a Swedish laboratory in 1751 by a careful, methodical scientist who looked at the demon's work and said, "This is not a curse. This is chemistry. Let me understand it." Some of them went to war, pressed into the barrels of rifles and the armor of tanks, and, in a strange reversal, briefly removed from the coins in American pockets so that they could be sent to the front instead. Some of them are in the turbine blades of the jet engine, carrying someone across an ocean at this moment, spinning in fire at temperatures that would melt ordinary metal, holding their shape, holding their crystalline integrity, making flight possible in a way that was impossible before we learned to use nickel to guard the heart of the engine. Some of them are in the battery of a car that its owner bought because they wanted to do something good for the planet, parked in a garage somewhere, charging quietly on electricity that might still be mostly from coal. And some of them, the ones on the seafloor of the Clarion-Clipperton zone, are still in their nodules, still growing, 1 millimeter per million years, in a darkness and a cold that has been undisturbed for longer than complex life has existed on this planet. Nickel is, in the end, a story about the impossibility of simple answers. Every version of this element that we have encountered in this story is real. The demon is real. The goblin of the mines, the trickster that poisoned men who trusted their own expertise, that promised copper and delivered death. The angel is real too, the invisible guardian of jet engines and surgical instruments and the batteries that might save us from burning the atmosphere. The villain is real, the element at the heart of a supply chain that is stripping forests and poisoning rivers and reshaping geopolitics in ways that ordinary people never see and barely understand. The innocent is real, the trace element in the root enzyme of a legume, the ancient biochemical necessity, the thing that life figured out how to use 1 billion years before we arrived and started making a mess of things. These are not different nickels. They are all the same element, the same atom, with an atomic number of 28, sitting between cobalt and copper on the periodic table, looking unremarkable, looking almost boring, waiting for you to look closer. The arc of nickel's human history runs from a curse to a necessity, from a demon's name to a periodic table number, from a medieval miner's nightmare to the beating heart of the 21st century's most important technological transition. And it is not finished. The story does not end here, because the demand is accelerating, and the easy deposits are thinning, and the ocean floor is waiting, and the recycling infrastructure is being built, and the phytomining researchers are in their fields with their strange little hyper-accumulating plants, and the battery engineers are in their labs trying to design nickel out of the equation entirely. All of this is happening simultaneously, right now, on the same planet, driven by the same human impulse, the desire to build things, to go places, to use the world, to take what the universe has scattered across space and time and planetary catastrophe and stellar death, and turn it into something useful. That impulse has brought us extraordinary things. It has also brought us to the edge of multiple crises simultaneously. The question that nickel poses, the question that this small, dull, unfairly overlooked element forces us to confront if we take its story seriously, is whether a species clever enough to find stardust in a coin is wise enough to decide what to do with it. The Saxon miners believed in Old Nick because they needed an explanation for suffering they could not otherwise account for. We have better explanations now. We have chemistry and geology and materials science and ecology and economics. We know what nickel is. We know where it comes from. We know what it costs. The question is whether knowing is enough, whether knowledge, this time, is sufficient. Whether we can look at that coin in our hand, that fragment of a dead star, that gift of cosmic violence, that product of 1 billion years of planetary geology and a few centuries of human ingenuity and a few decades of industrial recklessness, and decide deliberately and collectively what kind of story we want to tell with it next. The demon is in your pocket. What are you going to do with it?